Welcome to DAR Tutors. Today, we will explore key concepts in IB Chemistry Higher Level, specifically focusing on data analysis and redox reactions. We will cover topics essential for the IB-HL curriculum. We will begin by differentiating between accuracy, precision, reliability, and validity in experimental data. First, we'll establish a clear understanding of these critical terms for data analysis. Next, we will construct and use a reactivity series, learning how to write and balance redox half equations and full equations in acidic solutions. This section will provide the foundational skills for understanding and predicting chemical reactions. Then we will analyze the process of corrosion and sacrificial protection. Understanding these electrochemical processes is crucial for real-world applications. Finally, we will examine redox equilibria and electrochemical cells, focusing on the electrolysis of molten salts. This will connect our knowledge of electron transfer to the generation and use of electricity. Our first objective is to clearly define and differentiate between the terms accuracy, precision, reliability, and validity in the context of scientific measurement. Understanding these concepts is fundamental to evaluating experimental data. Let's start with precision. Precision is a measure of how close your repeated measurements are to each other. It describes the reproducibility of your results. In other words, a precise set of data shows very little variation. Now, consider accuracy. Accuracy is a measure of how close your measured value is to the true or accepted value. It describes how correct your result is. An accurate measurement, therefore, is one that closely matches the known standard. It's critical to understand that results can be precise without being accurate. Let's look at an example from a titration. This is a common misconception, so let's clarify it with a concrete case. Suppose we have a set of titration results, 23.45, 2340, 2350, and 2355 cubic centimeters. The range of these values is only 0.15 cubic centimeters. Because they are so close together, we can say these results are highly precise. The small spread in the data points indicates good precision. Now consider a second set of results, 2390, 2500, 2210, and 22.45 cubic centimeters. The range here is much larger, over 2.90 cubic centimeters. These results are not precise at all. The wide variation shows a lack of precision. Let's revisit set 1. Let's assume the true value for the titration is exactly 2300 cubic centimeters. Even though our measurements were precise, they are not accurate, as they are all about half a cubic centimeter higher than the true value. This demonstrates that precision does not guarantee accuracy. The consistent difference between the precise measurements and the true value is called a systematic error. This can happen if an instrument is not calibrated correctly, like a thermometer that always reads 4 degrees too low. A systematic error is a consistent, repeatable error that affects all measurements in the same way. Finally, let's discuss reliability and validity. Reliability refers to whether your experiment can be repeated by another person following the same method, and they would get results with a similar level of precision. A reliable experiment should yield consistent results regardless of who performs it. Validity is about whether your experiment is actually testing what it is intended to test. For an experiment to be valid, the method must be accurate and directly measure the intended variable with minimal variation. A valid experiment ensures you are measuring the correct thing. To recap, we've defined precision as the closeness of repeated measurements, accuracy as the closeness to the true value, reliability as the ability to be repeated with similar results, and validity as the measure of whether the experiment is appropriate for its intended purpose. These terms are the bedrock of collecting and processing data in chemistry. Let's now move into our second topic. Our objective is to establish and use a metal reactivity series, predicting the outcomes of single displacement reactions and representing them with redox equations. This involves understanding how metals compete to lose electrons. A reactivity series is a list of metals ranked in order of their chemical reactivity. The most reactive metal is at the top, and the least reactive is at the bottom. Reactivity in this context is defined as the ease with which a metal loses electrons to form cations. The more reactive a metal is, the stronger its reducing power, meaning it has a greater tendency to donate electrons. A metal higher in the series is a stronger reducing agent. This concept allows us to predict single displacement reactions. A more reactive metal will displace a less reactive metal from a solution of its ions. In other words, The stronger reducing agent takes the electrons from the weaker one. The general equation for this is metal X reacting with the ions of metal Y to produce the ions of metal X and solid metal Y. Let's look at an example from the IB chemistry text. The reaction between magnesium metal and copper 2 sulfate solution. We can write this as a chemical equation. The formula equation is Mg solid plus QSO4. Aqueous reacts to form MgSO4 aqueous plus Cu solid. Notice that magnesium displaces copper. Why does this happen? The reactivity series tells us that magnesium is more reactive than copper. This is the key piece of information for predicting the reaction. Now, let's represent this as a redox process. First, we write it as an ionic equation, showing the ions. This gives us a clearer picture of the species involved. Next, we identify spectator ions. These are ions that appear on both sides of the equation and do not participate in the reaction. Here, sulfate ions are spectators. The sulfate ions are simply watching the reaction unfold. The resulting net ionic equation shows the core redox reaction. We can then split it into two half equations, one for oxidation and one for reduction. This is a fundamental technique in electrochemistry. Magnesium atoms lose electrons, so they are oxidized. Copper 2 ions gain electrons, so they are reduced. Magnesium is the reducing agent, and copper 2 ions are the oxidizing agent. This confirms our prediction based on the reactivity series. To recap, we've seen how to use the reactivity series to predict single displacement reactions, and how to represent these reactions using formula equations, ionic equations, and redox half equations. This systematic approach is essential for solving problems involving metal reactivity. Let's work through another example to solidify our understanding of constructing a reactivity series from experimental data. This is a common IBHL question type. Our objective here is to deduce the order of reactivity, which requires careful interpretation of the experimental results. We have three metals, silver, lead, and nickel. We test them against solutions of their ions. A tick indicates a reaction. A cross indicates no reaction. The table summarizes our findings. Let's analyze it row by row, looking for patterns. First, consider silver Ag. The table shows no reaction with lead ions, Pb2+, or nickel ions, Ni2+. This means silver is not strong enough to displace either lead or nickel. Since silver cannot displace other metals, it must be the least reactive of the three. Next, let's examine lead, Pb. The table shows it reacts with silver ions, Ag+, but not with nickel ions, Ni2+. Let's break down this information to place lead in our series. The fact that lead reacts with Ag+ tells us that lead is more reactive than silver. However, since it doesn't react with Ni2+, it must be less reactive than nickel. Therefore, lead sits between nickel and silver in terms of reactivity. Finally, let's look at nickel Ni. The table shows it reacts with both lead ions, Pb2+, and silver ions, Ag+. This single piece of data is very telling. The fact that nickel can displace both lead and silver means it is more reactive than both of them. It is the strongest reducing agent of the three. This confirms our previous analysis. Putting it all together, our reactivity series from strongest reducing agent to weakest is nickel, then lead, then silver. So the final order is nickel, lead, silver. Now, the question also asks for the ionic equations for the three reactions that occurred. The first reaction we identified was nickel with lead 2 ions. Nickel solid reacts with lead 2 aqueous to form nickel 2 aqueous and lead solid. The second reaction was nickel with silver 1 ions. Remember to balance the charge. Nickel solid reacts with 2 silver 1 aqueous to form nickel 2 aqueous and 2 silver solid. The third reaction was lead with silver 1 ions. Lead solid reacts with 2 silver 1 aqueous to form lead 2 aqueous and 2 silver solid. To recap, we use the pattern of reactions to determine the relative reactivity of the three metals, placing the strongest reducing agent, nickel, at the top, followed by lead, and silver as the weakest. We then wrote the balanced ionic equations for each observed displacement. This structured approach is key to success in these problems. Now let's look at more broad applications of the reactivity series, particularly how metals react with water, acids, and carbon. Our objective is to be able to predict the products of these reactions based on the metal's position in the reactivity series. Here's a more comprehensive reactivity series. Let's use it to analyze the reactions of different groups of metals. First, consider reactions with water. The most reactive metals, such as lithium, sodium, potassium, and calcium, react vigorously with cold water. The reaction for sodium is: two sodium solids react with two water liquids to form two sodium hydroxide aqueous and hydrogen gas. You can see the sodium fizzing and moving around on the water's surface as hydrogen is produced. Metals lower down, like magnesium and zinc, react only with steam to form the metal oxide and hydrogen. For example, magnesium reacts with steam. Magnesium solid reacts with water vapor to form magnesium oxide solid and hydrogen gas. The metal glows brightly as it reacts. Metals like iron, lead, copper, silver, and gold do not react with water at all. This is why copper pipes can be used safely in your home's water supply. Next, let's look at reactions with acids. The reactivity series includes hydrogen. All metals above hydrogen in the series will react with dilute acids to produce a salt and hydrogen gas. Zinc is a good example. The bubbles you see when zinc reacts with hydrochloric acid are hydrogen gas. In this reaction, the zinc metal is reducing the hydrogen ions from the acid. The ionic equation clearly shows this. Zinc solid reacts with two hydrogen ions to form zinc ions and hydrogen gas. Half equations would show zinc losing electrons and hydrogen ions gaining them. Zinc is oxidized and hydrogen is reduced. In contrast, metals below hydrogen in the reactivity series, such as copper, silver, and gold, will not react with dilute acids to produce hydrogen. These metals are not strong enough reducing agents to reduce hydrogen ions. Copper will not react with dilute hydrochloric acid. Finally, let's consider reactions with carbon. Carbon is included in the reactivity series because it is a common reducing agent in industry. Let's see how its position affects metal extraction. Metals that are above carbon in the reactivity series, like sodium and aluminium, cannot be extracted from their oxides using carbon. They are too reactive, and electrolysis is required to reduce them. For these metals, carbon isn't a powerful enough reducing agent. However, metals that are below carbon, such as iron, zinc, and lead, can be reduced from their oxides using carbon. For example, zinc oxide and carbon. Zinc oxide solid plus carbon solid reacts at high temperatures to form zinc solid and carbon monoxide gas. This principle is used in blast furnaces to produce iron from iron oxide. To recap, a metal's position in the reactivity series determines its reaction with water, acids, and carbon. More reactive metals react with water and acids, while less reactive metals do not. The position relative to carbon dictates the most effective method for extracting the metal from its ore. By using the reactivity series as a guide, we can predict the chemical behavior of metals. Our next topic is corrosion. The objective is to understand the electrochemical process of corrosion, specifically rusting, and to learn about sacrificial protection. Corrosion is a significant problem, but electrochemistry provides us with solutions. Corrosion is the chemical or electrochemical attack on the surface of a metal. Rusting is the specific term for the corrosion of iron or steel. Some reactive metals, like aluminum and chromium, form a thin, unreactive layer of oxide that protects them from further corrosion. However, iron's oxide, rust, is porous and flakes off, exposing the iron to more attack. This difference in oxide properties explains why aluminum is so corrosion-resistant compared to iron. Rusting is a complex electrochemical process that requires both oxygen and liquid water. Without both of these, iron will not rust. The overall equation for rusting is 4Fe's plus 3O2G plus XH2OL, 2Fe2O3 bond XH2OS. Let's break this down into half equations. First, the iron metal loses electrons and is oxidized to iron O2 ions. This is the oxidation half reaction occurring at the anode, or area of oxidation. The electrons then flow through the iron to another area, which acts as the cathode. Here, dissolved oxygen and water gain electrons and are reduced to hydroxide ions. This is the reduction half reaction occurring at the cathode, or area of reduction. The iron 2 ions and hydroxide ions then combine to form iron 2 hydroxide, FOH2, which is rapidly oxidized by more oxygen to red-brown hydrated iron 3 oxide, our familiar rust. So, rust is ultimately iron 3 hydroxide, which is often represented as hydrated iron 3 oxide. Since rust flakes off, it continuously exposes fresh iron, perpetuating the corrosion. One of the most effective ways to prevent rust is sacrificial protection. This method utilizes electrochemical principles. It works by sacrificing a more reactive metal to protect the iron. In this diagram of a ship's hull, an iron object is connected to a block of magnesium or zinc, a metal higher in the reactivity series than iron. Because zinc or magnesium are more reactive, they have a stronger tendency to oxidize or lose electrons than iron. They become the anode and corrode in preference to the iron. The sacrificial metal donates its electrons to protect the iron. The electrons from the sacrificial metal flow to the iron, which is now the cathode. At the iron surface, oxygen and water are reduced, just as before, but the iron itself is not oxidized. By making the iron the cathode, we prevent its oxidation. To recap, corrosion, like rusting, is an electrochemical process requiring oxygen and water. Sacrificial protection is a method to prevent it by attaching a more reactive metal to the iron. This more reactive metal acts as a sacrificial anode, oxidizing itself to protect the iron cathode. This ingenious method extends the lifespan of iron and steel structures, from ships to pipelines. Our next objective is to master the systematic procedure for constructing and balancing complex half equations in acidic solutions. This is a core skill for any advanced study of redox chemistry. We will follow a 6-step method, using the example of the dichromate ion, Fn2, reducing to the chromium 3 ion, Cr3+. This method ensures that both mass and charge are balanced, a crucial requirement for any half equation. Step 1 is to simply write down the reactant and product. Step 2 is to balance any atoms other than hydrogen and oxygen. In our case, we have 2 chromiums on the left, so we need 2 on the right. Step 3 is to balance the oxygen atoms. We have 7 oxygens on the left, so we add 7 water molecules to the right. Step 4 is to balance the hydrogen atoms. Adding 7 water molecules to the right also added 14 hydrogen atoms. Since we are in an acidic solution, we balance these with hydrogen ions H+ on the left. Step 5 is to determine the total charge on each side. On the left, we have 14 positive charges from the H+ ions and 2 negative charges from the dichromate ion, for a total of +12. On the right, we have 2 Cr3+ ions for a total of 6. Step 6 is to balance the charge by adding electrons. Electrons are negatively charged. To balance a charge of +12 on the left and +6 on the right, we must add 6 electrons to the more positive side, the left. Let's check the final charge. On the left, 6 + 14 - 2 = 6. On the right, 6. The equation is now balanced for both mass and charge. This represents the reduction of dichromate ions. For an oxidation half equation, the process is identical, but the electrons will end up on the right-hand side. Let's try another example. The oxidation of sulfur dioxide, SO2, to sulfate ions, SO42. Here is our starting point. Steps 1 and 2 are to write the reactant and product and balance non-HO atoms, which in this case, the sulfur is already balanced. Step 3. We have 2 oxygens on the left and 4 on the right. We add 2 water molecules to the left. Step 4. The 2 water molecules added 4 hydrogens. We balance these with 4 H+ ions on the right. Step 5. The left side has a charge of 0. The right side has a charge of 2 from the sulfate ion and +4 from the hydrogen ions, for a total of +2. Step 6. We need to add electrons to the more positive side to balance the charge. Adding 2 electrons to the right side will change its charge from +2 to 0. The final equation, 2H2OL plus SO2G, SO42 AQ plus 4H plus AQ plus 2E, is now balanced. This represents the oxidation of sulfur dioxide. To recap, we've outlined a consistent 6-step method for balancing half equations in acidic solutions, ensuring that both mass and charge are conserved. This systematic approach is your key to confidently handling complex redox half equations. Now that we can balance half equations, let's learn how to combine them into a single balanced redox equation. Our objective is to master the ion-electron method for this process. This method ensures that the number of electrons lost in oxidation exactly equals the number gained in reduction. Let's work through an example from the IB chemistry textbook, the reduction of acidified manganate Sef ions by methanol. We are given the 2 half equations, which is the first step. Our goal is to combine these two half equations into one overall equation. To do this, we must ensure the number of electrons on the reactant side of the reduction half equation equals the number of electrons on the product side of the oxidation half equation. This is the central idea of the ion-electron method. In our example, the oxidation half equation has 6 electrons, and the reduction half equation has 5 electrons. The lowest common multiple of 6 and 5 is 30, so we need 30 electrons. We will multiply the first equation by 5 and the second by 6. Let's apply the multipliers. The oxidation half equation becomes 5 water plus 5 methanol yields 5 carbon dioxide plus 30 H plus 30 electrons. And the reduction half equation becomes 6 permanganate plus 48 H plus 30 electrons yields 6 manganese 2 plus 24 water. Now that we have the same number of electrons on both sides, we can add the two equations together. Adding the left-hand sides together and the right-hand sides together gives us this combined equation. Our next step is to cancel out any species that appear on both sides of the arrow. The electrons cancel out perfectly. This is the whole point of matching the number of electrons. Next, let's simplify the water molecules. We have 5 H2O on the left and 24 H2O on the right. We can cancel 5 from each side, leaving 19 H2O on the right. It's always easier to work with the smaller number. Finally, let's simplify the hydrogen ions. We have 48 H plus on the left and 30 H plus on the right. Canceling 30 from each side leaves 18 H plus on the left. Similarly, we cancel the smaller number of hydrogen ions. This gives us our final balanced overall redox equation. H3OHL plus 6MnO4 AQ plus 18H plus AQ. BCO2G. SMN2 AQ. 19H2OL. To recap, we used the ion-electron method to balance a redox equation by finding the least common multiple of the electrons in the half equations, multiplying accordingly, adding the half equations, and simplifying common species. This systematic approach is the most reliable way to balance complex redox reactions. There is another method for balancing redox equations, which can sometimes be quicker. Our objective now is to learn and apply the oxidation state method. This method focuses directly on the change in oxidation states of the reacting elements. Let's use the example from the IB chemistry textbook. The reaction between acidified manganate Sa7 ions and iron 2 sulfate. We need to identify what gets oxidized and what gets reduced. Step 1 is to identify the elements that change oxidation state. Here, manganese in MnO4 goes from +7 to +2, and iron in Fe2+ goes from +2 to +3. Step 2 is to balance the atoms that changed. In this case, we have one manganese atom on each side and one iron atom on each side. So no further balancing is needed yet. Step 3 is to find the change in oxidation state. Iron increases by 1. Manganese decreases by 5. To balance the electrons, the total increase in oxidation state must equal the total decrease. The least common multiple of 1 and 5 is 5. So, we need to balance the atoms with coefficients. The iron must be multiplied by 5 to match the manganese change. This means for every one MnO4 ion that reacts, 5 Fe2+ ions are needed. So, our equation becomes manganate reacts with 5 iron 2 ions to form 5 iron 3 ions and manganese 2 ion. Step 5 is to balance the oxygen atoms by adding water molecules to the appropriate side. We have 4 oxygens on the left, so we add 4 waters to the right. Step 6 is to balance the hydrogen atoms we just added. We have 8 hydrogens on the right from the water, so we add 8 H plus ions to the left. This is our balanced redox equation. It's often faster than the ion-electron method, especially when the half equations are already simple. The key is to correctly identify the changes in oxidation state and use coefficients to balance the total change. To recap, the oxidation state method involves finding the oxidation state changes, balancing the atoms involved, finding the least common multiple of the changes to determine the reacting ratio, and finally balancing the oxygen with water and hydrogen with H+. This alternative method provides another powerful tool for balancing redox reactions. Hello again from Dart Tutors. At this point in the video, we wanted to take a moment to encourage you. If you're finding this content challenging or want to delve deeper into these topics, expert tuition can make all the difference. Sometimes, one-on-one guidance is what it takes to truly master complex concepts. DART Tutors offers personalized online and home tuition for IB, A-Level, and IGCSE curricula. Whether you need support with a specific chapter, exam preparation, or just a comprehensive review, our experienced tutors are here to help. Contact us today to learn how our expert tutors can help you achieve your academic goals. Visit our website or call us to find out more. We look forward to hearing from you. Now let's continue with our lesson. Thank you for listening. Let's get back to our topic. We now move to a higher level topic, redox equilibria. Our objective is to understand how these equilibria are established between metals and their ions. This concept is the foundation of electrochemical cells. A redox equilibrium is a dynamic equilibrium involving electron transfer. This means the forward and reverse electron transfer reactions are occurring at equal rates. Consider a simple system, a copper rod placed in an aqueous solution of copper-2 ions. This creates an interface between a solid metal and a solution of its ions. At this interface, two opposing processes begin immediately. First, copper atoms from the rod lose 2 electrons and enter the solution as copper-2 ions. This leaves the 2 electrons behind on the surface of the rod, which consequently builds up a negative charge. This is the oxidation, or forward reaction. Q solid goes to Q2 aqueous plus 2 electrons. Second, the copper-2 ions already present in the solution collide with the surface of the rod. They gain 2 electrons and are deposited as neutral copper atoms. This is the reduction or reverse reaction. Q2 aqueous plus 2 electrons goes to Q solid. So we have a dynamic equilibrium. Initially, the forward reaction, the oxidation of the metal, might be dominant, leading to a buildup of negative charge on the rod. This negative charge repels new ions from entering the solution and attracts positive ions, which helps to increase the rate of the reverse reduction reaction. The system reaches equilibrium when the rate of copper atoms oxidizing to form Cu2+ ions equals the rate of Cu2+ ions reducing to form copper atoms. At this point, no net change occurs. This equilibrium determines the electrical potential of the electrode. The position of this equilibrium depends on the reactivity of the metal. For an unreactive metal like copper, the equilibrium lies further to the right. This means that the reduction of Cu2+ ions to form copper atoms is relatively easy. Copper-2 ions are relatively easy to reduce, making them a good oxidizing agent. The equilibrium lies further to the right, favoring the metal atoms. Now consider a reactive metal like zinc. If we place a zinc rod in a solution of Zn2+ ions, because zinc is more reactive, it has a stronger tendency to lose electrons. For zinc, the equilibrium lies further to the left. This means the oxidation of zinc atoms to form Zn2+ ions is relatively easy. Zinc metal is a strong reducing agent. The equilibrium lies further to the left, favoring the ions in solution. To recap, we've seen that a redox equilibrium is established at the interface between a metal and its ions. This equilibrium is dynamic, with opposing oxidation and reduction reactions occurring. The position of this equilibrium, which depends on the metal's reactivity, dictates the ease of oxidation or reduction and the resulting electrical potential. Understanding these electrode potentials is key to building and analyzing electrochemical cells. We now move to a practical application of redox reactions. Electrochemical cells. In this scene, we will define electrolysis and identify the components of an electrolytic cell. Our objective is to understand how we can use electricity to drive non-spontaneous chemical reactions. For a substance to conduct electricity, it must contain charged particles that are free to move. In metals, these are valence electrons. In solutions or molten substances, these are ions. An electrolyte is the substance that conducts electricity and is decomposed by its passage. This process of decomposition by electricity is called electrolysis. It is a non-spontaneous process and requires a constant input of electrical energy. Let's identify the key components of an electrolytic cell. Display figure R348 from the textbook, an electrolytic cell used for electrolysis. We've already defined the electrolyte. The power pack provides the necessary electrical energy to drive the non-spontaneous reaction. The electrodes, often made of inert carbon, graphite, or platinum, provide the surface for the redox reactions to occur. The electrodes are connected to the power pack. The electrode connected to the positive terminal is called the anode, and the electrode connected to the negative terminal is called the cathode. It is crucial to remember this connection. When current is passed, charged ions in the electrolyte move. Negative ions, called anions, are attracted to the positive anode. There, they undergo oxidation, losing electrons. Positive ions, called cations, are attracted to the negative cathode. There, they undergo reduction, gaining electrons. Anions to anode, oxidation. Cations to cathode, reduction. A helpful mnemonic is an ox-red cat. Therefore, the flow of current in an electrolytic cell involves electrons flowing in the external wires and electrodes, and ions flowing within the electrolyte. This is a key point. Electrons do not flow through the aqueous solution. To recap, electrolysis is a non-spontaneous process that uses electrical energy to decompose an electrolyte. The key components are the power pack, which drives the reaction, the anode, where anions are oxidized, and the cathode, where cations are reduced. Remember, the anode is positive and the cathode is negative in an electrolytic cell. This framework will help us analyze specific electrolysis reactions. Let's apply our knowledge of electrolytic cells to a simple example: the electrolysis of molten lead-2 bromide. Our objective is to predict the products and write the half equations. This will illustrate the basic principles of molten salt electrolysis. We're electrolyzing lead-2 bromide. When it's molten, the ions become free to move. This is why ionic solids don't conduct electricity, but their molten forms or solutions do. First, let's consider the cathode, which is the negative electrode. It will attract the positive ions, or cations. In this case, that's the lead-2 ions, Pb2+. Cations are always attracted to the negative cathode. At the cathode, the lead-2 ions gain electrons and are reduced to molten lead metal, which collects at the bottom of the cell. The half equation for this reduction is lead-2 ion plus 2 electrons yields lead liquid. Next, let's consider the anode, which is the positive electrode. It will attract the negative ions, or anions. In this case, that's the bromide ions, BH. Anions are always attracted to the positive anode. At the anode, the bromide ions lose electrons and are oxidized to bromine gas, which bubbles up and can be seen as a reddish-brown vapor. The half equation for this oxidation is 2 bromide ions yields bromine gas plus 2 electrons. So, the products of the electrolysis of molten lead-2 bromide are molten lead at the cathode and bromine gas at the anode. We've successfully predicted the products based on the charge of the ions. Let's quickly look at another example. What are the products of electrolyzing molten aluminium oxide, Al2O3? The ions are Al3+ and Ot. At the cathode, the positive aluminium ions will be reduced to molten aluminium. The cathode half equation is Al3+ plus 3 electrons yields Al liquid. At the anode, the negative oxide ions will be oxidized to oxygen gas. We need to be careful with the balancing here. 2 oxide ions yield oxygen gas plus 4 electrons. The overall equation for molten aluminium oxide would require us to balance these two half equations, which would result in 2Al2O3, 4All, plus 3O2G. To recap, for the electrolysis of a molten ionic compound, the cation is always reduced at the cathode to form the metal, and the anion is always oxidized at the anode to form the nonmetal. This is a straightforward and predictable process. This rule applies to all molten binary salts. Let's conclude by testing our understanding with 5 IB-style practice questions. Our objective is to apply the concepts we've learned to solve problems. These questions will cover data analysis, reactivity, corrosion, and balancing redox equations. Question 1 asks us to identify the least precise set of data and explain our choice. The key here is precision. Remember, precision is how close the results are to each other, so we need to look for the set with the widest spread. Let's find the range for each set. The range is the highest value minus the lowest value. For C, the range is 1.7 cubic centimeters, which is the largest. Therefore, set C is the least precise. It shows the largest variation between the measurements. Question 2 gives us reaction results for 3 metals. The table summarizes the outcomes. We need to determine the order of reducing power, from strongest to weakest. Let's deduce the order. Metal X reacts with Yin+, so X is stronger than Y. Metal Z reacts with Yin plus, so Z is stronger than Y. Metal X does not react with Xenon plus, so X is weaker than Z. Therefore, the order from strongest to weakest is Z, then X, then Y. Question 3 asks about a protective coating for iron. This is a sacrificial protection scenario. For the iron not to corrode, metal M must oxidize in its place. This means M must be a stronger reducing agent, or more reactive, than iron. Question 4 asks us to balance a redox equation in acidic conditions. Let's quickly apply the oxidation state method. N goes from +7 to +2, change of 5. S in HSO3 goes from +4 to +6, change of +2. To balance these, we need 2 MnO4 ions and 5 HSO3 ions. Apologies. There was an error in the calculation of oxidation states in the previous question. Let's correct question 4 and provide the full, correct solution. This demonstrates why it's so important to be precise and double-check your work, even in a video. Let's re-examine the oxidation states carefully. The oxidation state of Min is +7 in MnO4 and +2 in Mn2+. That's a decrease of 5. This is the reduction half. Now for the sulfur. In HSO3, hydrogen is +1, oxygen is +2. So sulfur is +1 plus S plus 3, 2 equals +1, which gives S equals +4. In SO42, sulfur is S plus 4 solder 2 equals +2, which gives S equal +6. So sulfur increases from +4 to +6. This is the oxidation half. Okay, now we have a decrease of 5 and an increase of 2. The least common multiple is 10. So we multiply the reduction by 2 and the oxidation by 5. This gives us 2 MnO4 reacting with 5 HSO3. So the initial balancing gives us this. Now we balance the rest of the equation. We have 5 hydrogens on the left. We can balance the oxygens first. We have 8 plus 15 equals to 23 oxygens on the left and 20 oxygens on the right. We need 3 waters on the right. This also adds 6 hydrogens to the right. Now for the hydrogens. We have 5H on the left from HSO3 and 6H on the right from the water. We need 1 more H plus on the right to balance. Balancing hydrogen with H plus. This is our balanced equation. Notice there is a single H plus on the product side. Our final question asks us to identify the products of electrolyzing molten lithium bromide. Using our simple rule for molten salts, the cation, Li+, will be reduced at the cathode to lithium metal. The anion, BRH, will be oxidized at the anode to bromine gas. We have now covered the essentials of data analysis, metal reactivity, corrosion, redox equation balancing, and electrolysis for the IB Chemistry HL curriculum. Thank you for your attention. Mastering these concepts is fundamental to success in your course.